Okay, good afternoon, everybody. I'm extremely happy, and it's a real pleasure to introduce to you our speaker of today, Margarida Telo da Gama. She's a professor of physics in the University of Lisbon in the Centro for Teórica and Computational Physics. She got her PhD back in 1982 in the University of Bristol in the UK, and then moved for some years to Cornell University in the US, and then back to Lisbon. Her current scientific interests, at least as they are stated in her webpage, are statistical mechanics of complex fluids and physics of complex systems. But as far as I know, in her career, she has addressed a broad range of topics, generally within statistical physics and condensed matter physics, more specifically in soft condensed matter physics, wet interpositions, liquid crystals, polymers, colloids, and so on. More recently, she has been working in topics as the Rodin folding, dynamics of epidemics in networks. Even I saw that she has a paper on the dynamics of language change, which I liked. So she has a very broad interest in many aspects connected to things that we do here at IFISC. She's part of many international boards and committees closer to us. She's a member of the board of the Division of Statistical and Non-Linear Physics of the European Physical Society, and she's also a member of the UPAP Commission on Statistical Physics. And last, I would also like to tell those of you that might not know that we are very happy that she accepted a few months ago to be a member of our external scientific advisory committee that was appointed by the Spanish National Research Council. So we are very pleased to have you here after so long, and the floor is yours.
Well, thank you very much. It's a real pleasure to be here. As Maxi said, it's been a long time since I've been hearing about the work done here in Mallorca. And in fact, I even heard about the work done by people like Maxi when I was still back in the USA. And for some reason, it took me all these years to come here for the first time, and he had to appoint me as an advisor to make me jump on a plane and make the long trip from Lisbon to Parliament. Well, anyway, for some reason or other, actually, I had never been here, so I'm really happy to be here, and I would have come even if you had not invited me to be on the advisory board. And I think I will start with a very small explanation. I think this is the title I gave you, and basically this talk some of you, the ones who went to physics, have seen part of it. I changed it, I made it shorter. I'm not going to fall off the floor this time because there is nothing to fall off from. Anyway, basically what I try to do is tell you about some recent work that bridges some of the work I did just when I was starting, and even some of the more recent work on complex systems. So this is really a talk on complex fluids, and in the end I will try to convince you that if you work on complex networks, you might actually add to some of these results that I will show you. But the motivation is really in soft matter, and I want to start off by setting off the scale. It's always nice to set off the scale, and I'm going to talk about things that can be realized in colloidal systems. And you can look at any definition of colloids, but basically I'm talking about particles that have a typical dimension of micrometers. And of course, you might recognize that picture. That's practical in nuclear physics. I want nothing to do with it except for artistic reasons. And also here on the other side, all sorts of interesting pattern forming systems on a continuum level. But I'll try to focus on this middle range here, where you have these synthetic colloids, 2 microns. They look like perfect hard spheres. In fact, one theoretician was saying the other day that people who work on hard spheres, or especially theorists who worked on hard spheres, was safe for a long time because there were no experimental systems, but now there are colloids, and they really do behave like hard spheres. Here you see some biological molecules, and here some synthetic colloids. These colloids are called now complex colloids because, by contrast with these, where the interactions are isotropic, these colloids can be tailored to have anisotropic interactions. And this is going to be central to what I'm going to say, because I'm going to try and model some of these structures or clusters that can be formed by colloids that have anisotropic types of interactions. Okay, you can see some viruses here, some blood cells, and so on. But I'll be talking about colloidal systems, and I already mentioned in the previous transparency that colloids played a very essential role in the early years of the 20th century when, by observation, Jean Perrin and Swap observed, measured how the sedimentation of these colloids occurred, and this apparently convinced the people who did not believe in the existence of atoms that atoms actually do exist. And much more recently, about 2 years ago, 2 other not Nobel laureates, but 2 physicists or physicists and chemists, I don't know. Peter Pusey from Edinburgh and Henk Hegerberger from Utrecht were awarded the prize from the European Physical Society Liquid Matter Division for work on behavior of colloidal suspensions. I want you to focus. This guy actually did see the colloids using a very basic and primitive microscope, and in fact, the recent work was due to the fact that amongst the techniques, but especially the Utrecht group, developed this scanning confocal microscopy apparatus, and they actually been observing colloidal systems, and for that reason they have been playing a very important role, not only in the statics, but especially in the dynamics, because also timescales are small, are much longer because these particles are big, and they can be seen, they can be observed, they can be registered. So there's a wealth of information that you can get from these systems, and then you not only do you check your theories, you can get ideas to develop new ones. So this is the sort of introduction that I would like to give you, and this is now closer to my talk. I want to talk about colloidal networks, and this is a kind of vague term, and I will try to sort of define it as I go along. I took this picture from a very recent issue of Soft Matter. I didn't even read the paper, so don't ask me what the paper is about. But the pictures speak for themselves, at least to me, and this is all I want to say. These are colloidal particles, and they are magnetic, so they have these anisotropic interactions. And depending on the ranges of these interactions, you can see structures which are cluster-like, maybe this is not very different from some atomic systems, but then you can see chains forming. And you can measure again using various techniques. You can measure things like order parameters, basically how these chains align and how long they are and so on. And also equations of state, in the sense that if this is thermalized, you can relate pressure to the density of these particles and so on. So there is really, quite apart from their visual attractiveness, some of these experiments and the fact that in colloids you can actually manipulate and tailor the interactions. There is quite a new range of possibilities that is open for both theory and experiments. And I'm going to divide this talk into only two sorts of topics. The first one, so I'm going to talk about equilibrium. I'm sorry, Max, it's in dead physics. It's almost lying physics. It's living, it's dying slowly. It's like colloids. So the equilibration is really slow sometimes. But I will start with some equilibration processes where these structures are assembled, but they are equilibrium structures. So they only depend on parameters that you can control, like temperature and density of colloids. And I want to start with a very, very simple case, which has some surprises, and I want to amuse you with some of the results. And to motivate the second part, which is perhaps less toy-like in terms of modeling. And but there is a connection, and I want you to see the connection. And then in the outlook, I'll make a connection between these two topics, and also between the random networks and some of the structures you can get out of those systems from them. So the question I'm going to ask is, if instead of having rods like a fixed length, or even polydispersed rods that you prepare in the laboratory, if you now self-assemble these rods, the question is, what sort of structures do you get? What sort of transitions do you get? And in particular, you know that if you have rods of fixed lengths, and if you colloidal rods, I mean, this is not either, just by entropic reasons, they can order, they align, they form nematic phases. And you also know in 3 dimensions what the transition looks like, it's weakly first order. And the question now is, how does self-assembly, equilibrium, I'll start with some examples from non-equilibrium self-assembly, affect the transition? What can you say? How can you control the structures out of these extra parameters? Because if you have polydispersity, usually you will have very monodispersed systems. But life is not like that, so even if you prepare these rods, usually, unless you prepare these spheres, I mean, most of these rods will be polydispersed. So you would like to know how this extra parameter changes the transition. One way to model polydispersity is very simple to say, look, this is a distribution, for example, of clay rods, and this is the length distribution. I should look on the parent. So this is the black curve. This is the parent distribution. There is a sort of typical rod lengths, but of course you have smaller rods and bigger rods, and you prepare these and you can then select them or whatever, but in most situations you have some distribution of rod lengths. And the question was, how does this affect these ordering nematic isotropic transition? Some pictures here. This is the parent, these are the rods. This is through light transmission microscopy, and of course this will go into, this is the isotropic phase that will actually phase separate into nematic. And of course these are the distributions in the various phases. But the surprises or not come later. Actually, I mean, this is just the nematic one forming after the phase separation. If you wait long enough, there is a second nematic phase that appears. And nobody really understands if that's just because the relaxation is much, much slower in this second nematic, or what's going on here. So there are two things. The transition becomes more strongly first order, and there are new phases that appear. They seem to have very different dynamics, at least very different time scales. If you look at these vials here, in this one, this is just nematic, and this is the isotropic. If you wait 1 month, I think that's what they say, there is a second nematic phase that appears, and this appears after a few hours. So clearly there are questions here that have to do with the fact that these things are long, they have time scales that you can control and study, but also they have more structure, and they can give rise to more diversity than the simple rods that Onzaga treated in his very seminal paper. Okay, so I want to simplify this because I really want to understand this a little bit better. So the first thing, I want to go to 2 dimensions, and this is not work of ours, this is work by a group in Argentina. This is just from one of their papers, and I just want to recall some of their results. In 2 dimensions, if you now simplify it even further, you put these things on a lattice. So these are rods of some length, but they're all fixed, so they all have the same length, on a square lattice. And of course, if you increase the density of rods, so this is the isotropic phase, you see as many rods pointing up as pointing sideways. They have no up and down, it's just 2 directions. These rods have no arrows. And you see that these rods will align. You find an ordered phase at a certain critical density. These things are athermal, only excluded volume is the only quantity here. So as you increase the density of rods, number of rods, they will have to pack, and they pack more efficiently if they order, so they order. And of course, if you ask yourself what the order of this transition is, it might not seem very obvious, but first of all, in 2 dimensions, this ordering transition is continuous. And on the square lattice, they need all the proper analysis. On the square lattice, you really only have 2 states. So this is an Ising type transition. They actually measure the exponents using proper normal, quite standard now techniques, and they found that these are Ising. But now if they put the same rods on a triangular lattice, of course now the rods can choose 3 different directions. So the exponents transition is still continuous, and you find 3-state quartz model exponents. Again, by the same group, you put it in a honeycomb lattice. Now the rods are not completely straight, but you can see here 3, 4 lengths 4 rods. And if you look at this transition, this is still 3-state spots. So you say that, okay, so if you align things on a lattice, you only have special directions, and the transition looks like Ising or quartz, because these are the number of states that you have, okay? So we started with this model. This is not completely historical, but anyway, we wanted to look at these colloids, remember? And we wanted to look at colloids that did not interact isotropically, but they did interact in some sort of an isotropic way. The most isotropic you can get is if you put on these spheres just 2 spots, and you allow them to interact. If these spots overlap, they gain some energy, and so there are sticky spots, only 2, and then if you put them all on a lattice, they can only form rods, either up or sideways, but now the length is not fixed. Now there will be a length distribution, and if you let these things equilibrate, this length is like polydispersity, but it's not quenched. It's not prepared before you look at the experiment. It's actually driven by thermal fluctuations, and it's equilibrium. Okay? So this is the simplest model you can get. I'll put them on the square lattice as before, and the difference is that now I have polydispersity, and I have a yield polydispersity. So this polydispersity results from the equilibration, from the equilibrium process. Oops. So you can do the mean field theory for these. I'm not going to bother you with the analysis. It's quite simple to derive the free energy, the length distributions, the transition, and you find a continuous transition in mean field. It's always continuous. You cannot, at least for this discrete orientation plot in 2D. And so this is, for example, remember that now, because you have an energy, you have a temperature where the system orders. Nematic is an ordered phase, like this. And this nematic phase will occur at a given density that is a function of temperature. Now, because the length of the rods, the average length of the rods, depends also on the temperature. So you can imagine that the temperature determines the equilibrium polydispersity. This gives you an average length, and then for a given length there is a density above which the system will phase separate, and will give you this type of ordered domains, okay, nematic domains. This is a simple simulation that we did, and this is below the transition, temperature below the transition, this is at the transition, this is above the transition, okay? So you can calculate the things. In these days we were interested in finding if we could see a signature of the self-assembly process, and this would be signaled by a maximum in the specific heat when the bonds start forming, even before the transition, that certain densities, you can actually see a bump in the specific heat before the system phase separates. So this comes from the bonding. And then the lengths of the rods has to grow sufficiently before they actually want to order, before they want to form the nematic phase. And the dots are simulations on a square lattice. The curves are this mean field theory, which on this scale looks pretty much, gives you the order of magnitude, so we thought we understand what's going on. And in fact, we concluded that at least at these intermediates are still low densities. Ordering enhances bonding in the sense that it occurs before and then the specific heat is even increases in the order transition. And well, the length distributions are exponential. There are two exponentials in the ordered phase and only one in the isotropic phase. The lines again are this mean field theory that I will not bother you with. And the dots are from the simulation. On this scale again, the agreements seem to be perfect, so as good as you expect. And these are the expressions actually for the length distributions. We calculate the order parameter. The order parameter here is really the number of monomers or bonds you have on one direction minus the number of bonds you have in the other one. So if you're above the transition, this is 0 on average, and if you're below the transition, this is different from 0, and it goes to 1 at 0 temperature. So this is the proper order parameter, and we have done this for two systems at two different densities. This is low density 2.2, and this is the high density. This is the order parameter as a function of temperature, and you see the typical sigmoidal curve, continuous transition. This is the mean field, which is pretty lousy here, had to fail somewhere. And these dotted things are what we expected. I mean, we assumed Ising criticality, and we just assumed that the transition did not change, that the polydispersity did not affect the order of the transition, and the fit did seem pretty good. Except the referees, I think they were the referees, because this paper came out exactly almost at the same time as ours, did the proper job, and the proper job was, I think I'll go to the next slide. For those of you who've done many of these things before, this is the Binder cumulus. This is actually the same order parameter that we defined before, just a different letter. This is from their paper. And the paper came out last December. And the exponents are two-dimensional calculation, not either two-dimensional calculation. And so the question was, to me immediately, does this polydispersity, this equilibrium polydispersity, change? Is the relevant parameter? Does it change the order of the transition from Ising 2D to percolation? And I'll say a few words about some of the things we're doing in that direction, but we didn't have to wait very long for a Japanese group that worked on very similar models, not exactly the same models. And I won't go into this, but this is one of the famous vertex models. It is the 7-vertex model, meaning that the only thing you allow are the configurations that are depicted here on this side. And so these are the sorts of things you can have on a lattice. So you have these dilute, disordered configurations, and then there is a phase transition to some ordered configurations. And these people did use a slightly different technique, density renormalization group, and this is Ising criticality. So clearly, equilibrium polydispersity does not, because these things are also polydispersed. You see here I have a chain with 3, and of course this figure is 4 of 2. So these chains are not fixed. Also, this is an equilibrium system, so this is also equilibrium polydispersity. But in this case, the transition is Ising. We might say that this is not an exact calculation, and perhaps. But I think I have a physical explanation for what's going on, and I think we want to.
Margarida, let me ask you a question. All these rods are one rod. These are not that they stick together. The polydispersity means that you have rods of length 1, 2, 3.
This is a rod of length 2.
Okay.
This is a rod of length 1.
And this is set from the beginning.
No. This is what's set from the beginning.
What is it that is?
No, this is a vertex model. So the way, I'm sorry if I went too fast. In the vertex model, what you allow are configurations with certain energies, okay? And so what they allow are these configurations. These are degenerate, okay? So are these. So these have an energy. This will have an end energy, this have a gain in forming the bond, this has zero energy. But in fact, they did it for several bond and ratio between the bond energies when we put two together. Okay?
So polydispersity is an effect of the dynamics. At the end, you get a polydispersity.
This is equilibrium polydispersity.
We talk about anneal polydispersity.
Annealed in the sense that it's equilibrium. It results from the equilibrium configuration. It's annealed only in the sense that I don't prepare the polydispersity and then look at if it phase separates. I have monomers, or in this case, okay, I have monomers. They have some interaction energy. They might have some.
I understood annealed.
Annealed might not be a very well. It's annealed because it results from equilibrium. So it's equilibrium polydispersity. That might be a better word. Annealed might not be. I don't do anything after I set interactions. I let the system equilibrate, and then I look at the results. I see if I change the parameters, T, basically, they grow the density of these monomers, okay, these bonds. And then I see at the configurations in the ordered phase, disordered phase. Here I measure the order parameter M, magnetization to the power 8, versus temperature, and it's a perfect straight line. So clearly, this system is also polydispersed. Clearly, in this case, the transition seems to be Ising. And I'm not going to go back. There is a difference between these two models, and but I want to use these. I'm going to speed up. I want to use these to introduce now the general question of percolation and ordering or phase transitions of the type easing or condensation, and how they do interplay. So one of the things that is missing from the previous model, and that we were interested in, that we put at the beginning, is the branching. I mean, if you only put two bonding lines, you can only form rods. And these are very nice, and we were interested in rods for many years because of colloidal systems and dipolar types of systems that they form chains, usually in the presence of external fields. But the more general problem is if you now, instead of two sticking spots, you have three or more. Now, these things can branch, you know, these rods can, or these chains can branch, okay? And so you can talk about percolation in the usual sense, and because these are colloids and this can be measured, also we have to ask questions about, can we actually reach equilibrium? Remember, all I've said now is about the equilibrium results. And so you have to guarantee that you find scales of what is required to reach equilibrium. Okay, so very quickly, again, let's just consider the general problem. The general problem is I have some colloids, and they do stick together. I didn't put the spots there, but imagine they have spots so they can stick together, so they can aggregate, and then eventually they can form an aggregate that spans the system. And I can describe these using percolation models, random percolation models, percolation models, and so on. But this is purely geometrical. This is just how I describe the clusters. If I want to go back to physics and to colloids, I need to put in time scales. And if I want to talk about gels or whatever, I need to really control or understand not only the time scales involved. There are several time scales, okay? So percolation is certainly a prerequisite for these structures in terms of gel formation, but there is another requisite, which is the bond lifetime, okay? But I'll get to that. It's also clear from experiments, I'm going back and forth, but you know, this is the one of the systems that this is from the 80s, I think, 79, okay? So this is from the 80s, and this is just gelatin and water. Gelatin and water, and there's only a gelation or percolation transition here. But now if you start putting some alcohol, the water and the alcohol will phase separate, the percolation is still there, or the gel forming, and gelatin is still there. But now, see how this gel transition seems to, depending on the concentration of alcohol, it seems to emerge from the critical point, or if you like, the critical point of phase separation to emerge from this percolation line, and in other cases it doesn't. And we want to understand a little bit better, if we can, how these phase transitions that are thermal phase transitions have to do with this gel forming, which is the structure of the fluid after all. So how does the structure of the fluid, and in particular the existence of giant clusters, networks, percolated fluids, affect the phase transition, not only in terms of its nature, but even in terms of the more basic question: does it compete with the phase transition and prevents it from occurring? Some work was done in the 80s on a very different system, but addressing this very same question. Rather than spheric interactions like we had before that drove the phase transition, Corneliu and followers for some years addressed a slightly different problem, which was just attractive interactions, so the normal type of condensation. And he asked himself the question, if I define clusters in some way, and the way I define clusters, by the way, is not completely free. It depends on the property I'm measuring, for reasons that I will mention as I go along, things that have to do with time scales of the processes involved. Okay? So for each property, if you like, there is a cluster definition. This is not given by God, it's not really but we know if there is a phase transition, we know what the critical clusters are. And so, if I define a cluster for a particular physical property, how are they related with the critical clusters if they do exist? I mean, if the system phase separates, how does the structure, and in particular, how do infinite clusters affect or not the ordering transition, the temperature, or even the nature of the transition? Okay, the simulations of an Ising model, this time a 3D Ising model. So this is just a phase coexistence of the Ising model, and defining the probability of bonding. This is a bond correlated model, so this is an Ising model, and then I define these clusters by defining a bonding probability, which I can write any way I like, basically, if it makes sense. And this is basically what this is. Dieter Hermann and Dietrich Stauffer again in the 80s, they saw that these clusters do coincide with the Ising clusters for a particular choice of this bonding probability. They went a little bit longer, as in Corneliu and so on, went a bit longer. And the statement is the following: if the bonding probability is driven by attractive interactions, then the formation of the gel is a prerequisite of the condensation, if it exists. And it does make sense, because forming the percolating cluster is a weaker requisite than actually condensing and forming compact clusters or whatever to have phase separation. Okay? And in these days, in the 80s, he still called this gel-sol. This is just an Ising model, so in fact, none of those phases are really gels. And this is where time will play a role, because, to have a gel, the way we know it, to have a property that whose viscosity diverges or that reacts elastically to external fields, it requires at least the bond lifetimes have to satisfy certain properties. Okay, so the bond lifetime is an important question, and it has to be longer than the observation time. So, if in an Ising model you find these clusters, okay, but the bonds form and reform so quickly it doesn't affect anything. You don't have a gel. You can have these clusters, you can say they percolate, but you cannot measure them in any property because the bonds are very fast. They don't really live for long enough. Okay? So, how do you increase the bond lifetime? It's really the bond lifetime is the energy of bonding divided by kT. And now this is the next and last. I want to distinguish between reversible and equilibrium gels, because I want to stick with equilibrium polydispersity, and the normal gels, which are irreversible processes. Most gels are really result from irreversible processes, so they really kinetic pathways are important. And one mechanism, in fact, has been shown recently that the generic mechanism to sync without anisotropic interactions is through an arrested phase separation. So you imagine your colloids, simple spherical colloids, they try to phase separate into colloid-rich, colloid-poor liquid vapor. And then if you go through it and you arrest the phase separation, you form these gels that are totally out of equilibrium. Okay? So there are many other ways of doing that in models. This is the LCA, but how can you, or does it make even sense to consider equilibrium reversible gels? And, well, basically we need some attraction, right? We need some attraction to the bonding. And now if you want to increase the bond lifetime, one thing you can do is to decrease temperature. But you have to decrease this temperature without heating Tc. So to be able to decrease the temperature in the one-phase region, you need to depress the critical temperature. Otherwise you hit the two-phase boundary line, okay? So, and this was, in fact, and these are real colloids that have these properties. They have spots, and they actually, in fact, this is one sphere and it's covered by lots of little spheres. So this is a 2-spot, this is a 3-spot, 4-spot colloids. These things exist. They don't exist in large quantities, but of course this has been modeled already by a group in Rome led by Francesco Shortino, and they've been looking at these model patchy colloids by simulation, also using some theory. But the models are very simple. Spherical hard cores and bonding sites. In this model, all the bonding sites are the same. And what Shortino, remember that I said, if you only have 2 economic form chains, even if the chains are of lattice, basically there's no energy left to condense. So chains, in that sense, have no attraction. If they're flexible, they don't even order into these liquid crystalline phases. So basically, we know in the chain limit, the critical temperature has to go to 0, if there is a critical temperature. We also know that if you put too many spots, I mean, this becomes more and more isotropic as you put more spots. So you can imagine that after a number of spots, you get something like the Ising type of phase separation. So the interesting range is really in this, and in fact, they've showed through theory and simulations that they can decrease the critical temperature, by, that's the number of spots. How did they manage to have a number of spots which is less than 2 or which is non-integer? They did a mixture of colloids with 2 and 3. And so you can go to 0 as this number approaches 2, okay? So you see, this is kind of known, and this is the structure of those systems. And what's interesting here is that as the temperature goes down, you can see that these systems become more and more jelly-like. I mean, you see lots of chains, but these chains have junctions. These chains have junctions, and also this system is, assuming that the simulations are equilibrated, these are equilibrium polydispersed chains, which are not linear chains or not only linear chains. They may have junctions defects, if you like. These junctions can have several types. So there is one way, this is the message from these sets of slides, there is one way of approaching forming these huge clusters at equilibrium in the one phase region. But we wanted to do a little bit more, okay? So we wanted to understand how the structure of these network fluids affects the phase transition. And so this is the final part of the talk. We generalized that model and did what is left to do. We already said that the most interesting regime is the regime between 2 and 3 spots, okay? And now what is lacking from the original model is that all the spots were equivalent. And we made one of them different, okay? So we just, this is a model which is very similar to the previous one, but now you have 2 spots of one type and 1 spot which is different, and we completely control the interactions. We can switch on or switch off unlike interactions, like interactions, and so on. Okay? This is relevant for the dipolar fluid, which is one of the things that has been behind some of this work in our group and also in the group in Rome. It's very important for other associating fluids. You'll see that it generalizes all the conditions and requirements of condensation of these self-assembled fluids, but it's also by itself a model which is for the criticality of linear branch and even hyperbranch polymers. And here there is a connection with random networks and other networks which are not so random that I want to sort of mention at the end. So the generalized model has these 3 ideal limits. Ideal meaning that do not condense. They don't have two-phase separation. Linear chains, they can form, but you know they cannot. If you don't, if you switch off the BB interactions and the AB interactions, only leave the A interactions. These chains can, they do not condense. Okay, if they're very rigid, you could have some of that pneumatic transition, but these are Gaussian chains, so these won't even form a pneumatic phase in the model anyway. This is the opposite limit. Now you switch off the A's. There are 2 A's and 1 B. Okay, you switch off the A's and the AB's, and now all you can form is dimers. Again, the dimers do not interact, so then you have ideal limits, no phase separation. And this is the hyperbranch limit. This is the same system, but now you switch off the light interactions. You only allow the A's to interact with B's. What we form are polymers that are the most branched. That's why they call hyperbranched polymers. You only have a one bonding probability between unlike sites, and these are hyperbranched polymers. All these three limits are ideal, so we know what we're doing. We also can, if we look at how the coexistence arises and interplays with this, we can also make a very strong connection with the structure of these network fluids. And this is what we did in about a year ago. And here is the critical density, here is the critical temperature. This is using a theory which has been derived by Wertheim 20 years ago, but I'll show you some simulations afterwards. But just let me show you first the overall picture. So if we look at the chain limit and we switch off the BB interactions, we see that the critical point exists as long as you switch on those interactions. And if you think of two-way chains, that if they can bond through B bonds, well, they form an X-like junction. So we call these X junctions, and they go down to zero in terms of critical temperature and critical density. In polymers, if you know polymer criticality, the critical density goes to zero when the polymer chain goes to infinity, just because you cannot have more packing considerations. Forget the next two. So these are the types of chains we find when we look at the B bonds. So the transition is driven, it's a normal transition, it's driven by condensation of B junctions. Since the chains are not condensed, we can look at this in a more simple ways to look at the junction of the defects, and it's the defects that condense. We have a phase which is rich in X junctions and one phase which is two network phases. We think, we're going to show you that in fact we have two phases, two network phases. Okay, this is the other limit. We now have still A chains, no B interactions, BB interactions, but we let the A's interact with the B. And now the surprise was that the critical temperature actually goes to zero even if the AB interactions are attractive. So if we start from zero, switch on the AB attractions, these A chains will not condense until a finite fraction of AB junctions occur. And so this is a Y junction. This condensation requires a finite threshold or a finite fraction of bonds. Okay, this is interesting because it actually makes a connection with dipolar fluids and with some work, very elegant paper by Safin in Science that appeared in 2000. And we can distinguish two types of junctions, attractive and repulsive junctions. And this is the critical point that we found that occurs only if this interaction is greater than the main chain interaction divided by 3. And we find two types of condensation. One is the two surprises. It is, first of all, one thing is the AB interaction. The other thing is the interaction of this junction. To make this junction, we have to break the ring and we have to put an AB there, okay? So these junctions can condense in two ways. Either through entropic reasons, we can make this junction energy still repulsive, but they still condense because by entropic reasons, the chains like to have junctions. And this is what Safin had predicted. But we can also see that there are energy-driven junctions because we can make this EAB more attractive, okay? So now the final question is, okay, so we find that at the critical point we know the structure of the fluid, and what we would like to know is below the critical point, when the transition becomes first order, what does coexist? Do we have two network fluids? Do we have one network? Network means an infinite cluster. With a dilute fluid with finite clusters, or what? So you need to look at percolation. I'm not going to bother you. We actually had to, Zachariah really solve this percolation problem for these systems. This is a little bit more complex than the fluoride, but using the same assumption that there are no loops, you can actually, you have two bonding probabilities, so the probabilities are not independent, but if there are no loops, you can actually calculate the percolation lines. You can make a connection with thermodynamics, which is important, through these bonding probabilities that this theory of Wertheim gives you. So given the temperature and the density, we can calculate the phase diagram, we can calculate the percolation line through these routes. And so these are some simulations for the association. So in these limit low densities, we're doing quite well. And this is a summary of the results, okay? So this is temperature, this is density, this is a system that has AA interactions, okay, two sides array, AA interactions, no BB. And then we have a cross interaction, which is about the size but smaller than the AA interactions. And these are the simulation points. This is temperature, as I said, this is density, and this is the phase diagram. This is the simulation phase diagram, squares, this is the theoretical one, these are the critical points. And this is actually the percolation line that I showed you before, well, didn't show you before, but that Zemaria calculated. This is the maximum in the specific heat that will signal when these bonding processes are important. And what you see here, and answers the question that I was asking before, the critical point is here, the percolation line is on the left, so around the critical point really have coexistence of two network fluids, two fluids that actually have giant clusters. They are in the percolated regime. So, okay, now this is the final point, and we have a phase transition if I go back. Okay, so this is a normal condensation transition, we think, but that's what we have to figure out. We have a percolation here. This scale for these parameters is still, these points are quite separated. But what happens if I start lowering these quantities, that the critical point will go to the left, and the percolation line cannot go maybe density, so these 2 points will approach, and this is work in progress, so we're trying to figure out if this transition is still Ising-like, and it seems that it's Ising-like for most points. We have a point here which seems to be quite different, but presumably, I think we don't have an integrated system. I want to finish with a completely different problem that I'm not going to bother you about, but one of the funny things we did was actually quite funny. We could not actually calculate the first distribution functions to this generalized model, but we invented an effective model which is marvelous. I mean, it's as good as the real thing compared with the simulations of the real model. And these are just cluster distribution functions, number of clusters of size S, independent of which bonds are in that cluster, just counting the number of particles, okay? S is just number of particles, and the number of clusters of a given size. And at least in the non-percolated region, this effective model is quite wonderful. And this is more or less it. I want to just finish with an outlook. I think equilibrium self-assembly, and I try to stay under equilibrium conditions. I think I showed that here at the top. It's very difficult to stay under equilibrium in these gel systems. But anyway, equilibrium self-assembly is robust because it's equilibrium, and if you break it, it will try to form the same structure again. So it's also quite tunable. You can get different structures by changing slightly the parameters, the ratio parameters. And there's lots of structures. You can get them almost. And you can get them, what I said, if you forget the time scale, what I said is kind of relevant at the atomic scale as well as at the colloidal scale. So this is a mechanism that works for a large range of particle sizes. The polydispersity, rather than be looked at as some nuisance, can actually be very useful to control some of the structures of these systems. I think it was also clear that non-equilibrium and percolation are things that are very relevant if you want to look at these network fluids. And finally, I want to say that there's a very strong connection between quite a few, all of the things I said and network theory. The system with equal sides, the distributions, the percolation, and so on, can be mapped exactly to random networks. The hyperbranched polymers correspond to bipartite networks, and Sergei Dorogotsev told me, after we did all the things by hand, that these models actually, the generalized model corresponds to what the mathematicians call colored networks, colored random networks. They're still random. They get less and less random as you put more stuff into them. But so, at least, this is a nice framework that has, it's quite relevant to the structure of some of these systems that are polymeric and gel-like. And I think that some cross interaction between these two fields can be very fruitful. And I didn't say it, but going back to the first, if you remember the toy model, I think the generalized model will actually help us to distinguish To answer one question, I told you equilibrium polyviscosity in some cases seems to affect the phase transition, in others it seems to not to, and I think we can actually look at stability of the fixed points with this generalized model. I'm not going to tell you why, because this is still working for it, but I'll answer questions anyway. So, thank you. This was actually work by José Maria Tavares. He's a former PhD student of mine. He did all the work on dipolar fluids, and in fact we were driven to do these systems because dipolar fluid was really too complicated. And Paulo Teixeira was a student, a master student of mine who returned to Lisbon. Shorting is the head of the Roma group that did the simulations. Now José Maria is presently in Rome. They're actually still working on this. I thank my foundation for lots of euros, and of course I want to thank the police.
Thank you very much, Margarida. Questions, comments, criticism? Telo, you had a lot to say during the talk. You had a lot to say during the talk. We could not hear Margarida.
Well, I mean, one question is, first, what is a color network?
A color
The network
network.
does have correlations.
No. A color network is. I don't know. I've learned that only very recently. But I was going to put a few slides on the network. The color network is a network that has more than. If I go back to my model, I think I can explain a little bit better. Okay. What makes this model so annoying? I mean, if this model had 3 equal sides, this would be the clustering properties, the distribution functions could be calculated using the random percolation. Random percolation is exactly applicable, and this would be a random network. What makes this non-random in that sense is because by having different sides, you now have 3 probabilities: PAA, PBB, and PAB. Okay, but the sides are independent. That's the randomness. But there is a closure relation because PA has to be PAA plus PAB. So these 3 probabilities are not independent. So this means there are some correlations. And a colored random network is exactly a network that is trying to describe these types of correlations. And they're called colored because, like in the percolation problem, what we want to find out the size and distribution of the clusters independently of what bonds I switched on. How many AAs, how many ABs. I just want to know how many clusters of size n I have. Okay? So the mathematicians call it a colored random network because they assign a hidden color to these spots. And then in the end they forget the color when they calculate, but it's exactly the same type of problem. So these correlations are important in these chemical systems. They just sort of were thrown out at us. I don't know what driven the mathematicians to put these. This is a good question for me if I turn it around. Why the mathematicians had this model in mind, I don't know. We came to the model through the physical or chemical motivation. But the model is exactly the same. And the randomness just signifies that the sides are independent, and also there are no loops after the random.
No, the code also implies that
Code implies more than one bonding from
more important, not the fact that, for example, the probability of bonding A to A is larger than A to B.
No.
or
You can have any combination.
Just
then everything depends on a matrix that I did show you, not show, but there's an eigenvalue that gives you the maximum. When it's 1, gives you percolation line. That's exactly what they do with the color random graph.
And the second question is, you didn't say so much about this effective model that predicts all the results. But even if you don't want to disclose the model, can you just tell us what are the important properties that allow you to predict?
I'll tell you. See, I don't know if any of you have read the Florian Stockmeyer, but calculating these cluster distributions is a huge, horrible combinatorial problem, okay? Now, if you now try to do the same problem with different probabilities, this is it sounds changing the A's and the B's, and then it's totally possible. Then I spent 4 or 5 months doing that. And so I came up with the idea, which he didn't believe, but now he then refined it. It's one thing we can do. We cannot calculate the distribution function, but we can calculate from this kind of structure and also from random networks or colored random. We can calculate the moments of the distribution, so generating calculate moments of these distributions, okay? So we don't know the distribution, but we can know the first order moment, the second order moment, the third order moment. And now we say the following trick. The following trick is close to percolation. If you look at the equations, if you look at the equations, the clusters are big, and they are dominated by these larger eigenvalues. Even before there are two eigenvalues, this has two eigenvalues, and there's an eigenvalue that is bigger the cluster, you sum the series, and there's this eigenvalues to some power, and so of course the distribution is going to be dominated by the largest of these eigenvalues. So the idea is to assume that the system is described effectively by some model which has a bonding probability and the number of sites of functionality which is determined by matching the moments that we can calculate exactly to the real model to a model with all equal sizes and with the same moments. So the result is we get a functionality which is non-integer. We preserve the percolation threshold because that comes from the second moment. The model is exact at percolation. And so we then use Flores. Well, Flores has some factorials and so on, but we know how to do the continuation, get Gama functions and blah, blah, blah. So we can actually write the distribution functions in terms of this effective functionality, which is non-integer, and this probability that comes from matching the moments of the real distribution, which we can calculate without knowing the distribution, to the distribution, to the moments of the distribution with equal sites with this non-integer functionality that comes out from it. And it's exactly percolation, and it seems to be, that's the surprise, I mean, it's that we expected, but it describes the non-percolated phase almost exactly. Of course, in the percolated phase we have problems. Oops, I want to go to the end. Oh, never mind. I think I'm going back, yes. Never mind. I don't. Just wanted to show you the last picture because these are most of the points that are shown there are below the percolation for those systems, and these are simulations. Okay, all the dots and so on are simulations. This is the percolation density for this temperature. This is at a given temperature. Should be written here, it's not. But this is the density at which percolation occurs for this system at this temperature. These are simulation points, and this is the effective model. And you know, the dots are, it's almost embarrassingly too good. This is beyond percolation, and everything breaks down. But below, we expect good agreement below percolation, because that's how the model is built. But we were a bit surprised that we got things for small clusters, because in this, the model is expected to be good for large clusters. And then, you know, if you really refine it, of course it cannot be exact at percolation, because this is no loop, you know, and percolation in 3D has slightly different exponents. But it's also very good for the small ones, and that's, I think we know why. I think that in these small clusters, the way decides so that the system actually has very little loops as well. I mean, it costs too much energy to bend the stuff. So this is really a no-loop type of approximation, and it seems to work too well. We don't understand all the details, and Zema didn't believe it, but it actually works very nicely. He did calculations, so I'm not responsible for it.
Still, I haven't got the physical reason why, in the simple model in which you have two bonding sides equal, why do you have this percolation type exponents, and then with apparently the same model you get the icing model? Is there any explanation for that? Or?
I think I have one, but I don't have the numbers. I'm going to give you the physical explanation. The numbers will have to weigh the calculations. I think if I show you the pictures, I mean, the Japanese don't believe it, but I think, I don't know about the Argentinians.
You can have here a number to try.
Okay. In my model, the model that I need as Lopez, I think that's his name, I forget now, the two group. They have quite a number of papers in these simple, very simple models. Because this has connections with the car parking problem and dimers, absorption dimers. So there's a lot of work on these two-dimensional sticking rods on a surface, okay? So they have a lot of problems, and they have never done the polydispersity. They got the idea, I'm sure, because they repeat phrases from our paper, even before it was published. Even the way, and there's a fight with another referee, because they call it kinematic isotropic transition. The referee thinks it's not, because it's really too stable. Anyway. But anyway, their work was very nice, and it actually gave me lots of ideas. When I looked at the Japanese, look at these pictures, and I think this is not fair, but try to find the difference between these and the configurations allowed in the previous model. Previous model is, remember, just two spots, you can put two spots, they just cannot occupy the same vertex. And there's a gain in energy if there is overlap, no energy if there is no overlap between the spots. Okay? You can have T's and L's in our model. They cannot. If you look at the configurations that they allow, they disallow T's and L's. So in a way, if you look at, I think the physical problem is this. You have these rods. They have an average size which is determined by the equilibrium distribution. Okay? Now, in the vertex model, these rods cannot touch. And not only, they cannot overlap, but they cannot touch. Because you cannot have T's. You cannot have something like that. So you cannot percolate. So this system is really like the fixed size. It's really, you cannot percolate. When the rods get sufficiently large, they have to water, but they still don't percolate because you cannot jump from, rods will only become infinite at t equals 0. And because you disallow these junctions in this model, you cannot percolate. If you now think of the other model, it's still surprising, but if you think of the other model, we don't disallow T's. We don't give it any energetic advantage, but entropically they will appear. They don't appear in our Winfield theory. We really trying to modify the Winfield theory to give you this extra. But in the other model, we allow a rod to sit here. Two spheres form a bond, and then a third one can approach. By entropy, it will happen. So what I think is happening is that the percolation is occurring before the ordering transition. Now the real question is
this true?
Yes. Is this true? One question. The other question is, if it is true, is which one wins? Is one really stable and the other one unstable? And you switch on one. So with the simple model, what we're going to do, and I'll tell you what we're going to do, it's quite simple. We now have 4 spots, 2 A's and 2 B's. We put it on a square lattice. And instead of attractions, the A's will attract each other, so they form rods. And the B's now either don't interact or they repel. When the repulsion is infinite, we can mimic the set of vertex. It's not exact matching, we've been looking at it. But we can mimic this vertex model. If they don't interact, we have the old model, just with the A's. And we can look at the critical point and see if it changes for a certain value, if the universality class changes for a finite value of repulsions, or if it's always percolation for any finite repulsion. We don't know the answer. I have arguments to favor one scenario or the other, but they're all just very qualitative. They're not. I think we need to do the calculation. There is some competition that if any of you knows the answer, then we don't do the calculations. If you know which fixed point is stable, we don't have to do the calculations. It's very standard now. We didn't do it because I believe it was Isaac. But now we've seen that it is not. I think we want to go back and actually, I think we have, the general model allows us to go from one end to the other. And to check, at least numerically, if one of the fixed points is stable all the way through, or if it becomes stable halfway through. I don't know. I really don't know.
Okay, is there any other urgent question? Well, if not, we can continue discussing with coffee outside. Thanks again.